There are three principal sources from where the heat in our body is generated or comes from. After all, our body temperature is 98.6 degrees Fahrenheit. That's almost 100 degrees inside of us. It's certainly not 100 degrees in this room. So where's all this heat coming from? The major source is cellular respiration, because we know that as sugars are broken apart with oxygen to produce ATP, in fact, 60%, more than half the energy contained in a sugar molecule, goes off as heat, rather than being converted into making ATP. Only 40% of the energy within a sugar molecule actually creates ATP. You'd say, when did you tell us that? Page B3. Anyhow, a second source of heat in the body is muscular activity for two reasons. When you start to exercise, not only does that speed up the rate of cellular respiration because you need more ATP in order to make your muscles work at a higher level, but there's also frictional heat. Remember, we experience what we felt when we rub our hands together, how hot they get? So the very fact that you're moving your body, there's all kinds of moving parts and things sliding over one another that generate frictional heat. The third source of heat, we said, is the very process of processing food. It takes, there are biochemical reactions, enzymatic biochemical reactions that are involved in digestion of food into nutrients, absorption of the nutrients in your body, processing of the nutrients largely in your liver, storage of these nutrients, converting sugars into glycogen and amino acids into proteins, and this generates heat as well. So even if you were cold, even just eating a cold candy bar would help warm you up. Okay, and then on page C15, the three major ways that we get rid of heat. Now, again, in chapter 25 of your textbook, and I do recommend you look at the book, it actually enumerates about 6 different ways that we lose heat. So there are three major sources manner in which we get rid of heat are radiative heat loss, evaporative heat loss, and the very process of exhaling. In brief, what's radiative heat loss? It's the tendency of heat to flow from an area that's warmer to an area that's cooler. Since our body is almost always warmer than the air around us, we're always losing heat to the surrounding cooler air. The only time that doesn't happen is if the air around us is hotter than we are. But it's pretty rare that we have days that are 100 degrees or warmer. Okay? That's not common here in Los Angeles. It's not common in most places. So we wrote increasing heat temperature would reduce radiative heat loss, but as the air temperature around us goes down, that increases radiative heat loss. Our body can affect physiological adjustments to the rate of radiative heat loss by controlling how much warm blood flows through our skin. By dilating the vessels in our skin. Vessels in our skin are called cutaneous vessels, meaning the skin. That increases the flow of warm blood near the surface of our body, increasing radiative heat loss. If we want to reduce the rate at which we're losing heat to the surrounding cooler air, our vessels constrict, reducing the flow of warm blood near the surface of our skin. Does that make sense? So that's how our body can affect physiological adjustments to how quickly we lose heat to the surrounding air. Evaporative heat loss. Okay, all of us, before you ever took this class, know that when you're hot, you sweat. But what we tried to explain last time is how does sweating actually cool you down? If you simply say, well, when you sweat, you get cooler. Yeah, how? Did we explain it? I tried to. We said that the heat of your body is transferred to the water that is released onto the surface of your skin. And as that heat warms up the water, it causes the water to go from liquid to vapor. Just like heating a pot of water, where the heat is transferred to the water, causing it to bubble and then go from a liquid state to a vapor state. But in order for this heat to be transferred, in order to get rid of this heat, the water, the sweat, has to actually evaporate. It has to go from a liquid to a vapor state. And we learned last time that that can be mitigated, that can be affected by the humidity of the air. The more humid the air, the slower the rate of evaporative heat loss. So that's why, and this is why it's important, this is why when it's humid, people sweat and it doesn't evaporate. And so they're not getting cooler. It's very uncomfortable to be in a humid place, even if it's not even that warm. But it's uncomfortable. We can't get rid of the heat. The third way that we get rid of heat is simply by exhaling. We exhaled on our hand. We felt that the air we exhale was warm and wet. Every time we exhale, we lose both heat from our body and we lose water as well. We mentioned that we don't control our breathing per se, but those animals, such as dogs that cannot sweat, actually have these shallow breaths called panting, not for the purpose of taking in more oxygen. They're not inhaling the air all the way down into their lungs. They're just inhaling it into their mouth and out their mouth, into their mouth and out their mouth to get rid of heat. So that's they're using that method to get rid of heat. And that takes us to temperature regulation. Now, as always, there's the book. Where does the book cover it? So it's, again, chapter 25. Let's just show you the book real quickly. I feel like I'm putting plugs in every class meeting to do this. Right here, heat and energy balance. Because, and then on page 1002, metabolic rate. Ooh, body temperature homeostasis. And then it talks about heat production. And look at that, mechanisms of heat transfer, conduction, convection. We didn't even talk about those, but we did talk about radiation and evaporation. And then, what I'm about to talk about right now, the hypothalamic thermostat. And then at the bottom, thermoregulation. And look at this, ooh, a flow chart. And this is talking about input signals and output signals and effectors, because that's how I'm going to explain it. All right, so this is chapter 25. That would certainly be useful. Let's show you another resource to help you. So you right here, we're not going to play this whole thing, but just to show you, right here under thermoregulation, we click it. And if you go to animation and then click narrated and hit play.
Normal body function requires a relatively constant body temperature, which is regulated by the body's thermostat, a region of the brain called the hypothalamus. The hypothalamus generates a temperature set point for the body and appears to be the major site for the integration of temperature information. When the body's temperature is warmer than the set point, the hypothalamus sends instructions to various organs to cool the body down. When the body gets too cool, the hypothalamus commands the body to do the opposite and perform a warming response. Blood vessels are some of the targets under the control of the hypothalamus. For example, when the body is cooler than its set point, the hypothalamus triggers blood vessels in the skin to constrict. The constriction prevents blood from circulating close to the body's surface and thereby reduces heat loss to the environment. When the body is too cool, the hypothalamus also stimulates shivering. The repeated contractions of muscle fibers generate heat in the body. The hypothalamus controls an endocrine organ called the thyroid gland.
All right, well, you can obviously watch that because that's exactly what we're going to be talking about right now. So between the book and the videos, you've got lots of resources. You just need to spend like, hour, a couple of hours a day learning all this. All right, all right, so back where we were, the Thermoregulatory Reflex Center, so page C15. It is a control center in the hypothalamus of our brain. We'll learn more about the details of brain anatomy, physiology later in the course. And let's show you a model for how we're going to approach this. Look on the previous page, C14, and on the previous page, I think we looked at this at the end of class last time. This is our model. This diagram looks amazingly similar to what we saw on page, I think it was C8. C8 was our model, our paradigm for a homeostatic control center. Anybody remember that? This was page C8. I'm sorry, C6. This was our model on page C6 of homeostatic control mechanism and a negative feedback response. Did I say it was important to understand homeostasis and a negative feedback response? So on page C14, here's the control center, and it operates as if there is a set point, and it tries to maintain the temperature of our body at approximately 98.6 degrees Fahrenheit or 37 degrees centigrade. Now some of us run a little bit cooler than that, our set point. Some of our set points a little bit higher than that, but there is a normal range. Because as we've said, when you go to a doctor's office or you're admitted into the hospital, one of the first things they do is they stick a thermometer in your mouth, and your body temperature better be within the normal range. We have learned that there are sensors all over our body that sense or monitor all kinds of different aspects of our body, including temperature. And these are called, in the case of monitoring body temperature, they're called sensory neurons called thermoreceptors. These thermoreceptors relay information continuously along a sensory or afferent pathway to this temperature control center in the hypothalamus of the brain. This provides what's called the input signal. We learned back on page C6 that the job of a control center is to compare, same word I wrote on C6, it compares the actual body temperature with the desired body temperature, the set point. If they match, it's a beautiful thing. The control center doesn't have to do anything. But if they don't match, this control center will send an output signal along an efferent or motor pathway to those effectors, those effector organs that can correct and compensate and bring our body temperature back to the desired set point. So we learned that there are many effectors that are involved in maintaining our body temperature, including the blood vessels in our skin, the sweat glands in our skin, right? Blood vessels can affect radiative heat loss, sweat glands can affect evaporative heat loss, skeletal muscles, increased activity generate a lot of heat, as in the case of shivering, and there are a number of endocrine glands that secrete hormones that affect metabolic rate and therefore heat production. Now, an analogy of what we're going to say is depicted right here. This is kind of an old-style thermostat. This is an older picture because all the modern thermostats in your home or your apartment are digital. But the concept is the same. On the thermostat in your home or apartment, you can set the set point at whatever you want. You want to set it at 72, it'll maintain the temperature in your house at 72. You want to set it at 75 or 68, whatever you set it at, that's what it's going to try to maintain. Now, when I say it's going to maintain the temperature, here's how that works. If you set the temperature in your house at 72, and let's say at night it starts to drop below 72, so then all the thermostat does is it's comparing the actual temperature in your house with the set point. If it becomes lower than the set point, it turns on the heater. The heater turns on, and it stays on until the temperature in the house gets at least to 72, or usually actually it's got to get a little bit above 72, above what you set it at before the heater turns off. If let's say during the day, the temperature in your house starts to get higher than 72, once it gets maybe 73 or 74, the air conditioning will click on. And it'll be activated to cool the house back down, to bring it back down. Now, the way this is actually working is like this. Whatever you set, let's say you have the setting of your thermostat at 72, the actual temperature of your house does not stay exactly 72. It oscillates around the 72. The actual temperature of your house is going to oscillate around whatever you set it at. We say that it's in a steady state. You'd say, I don't get that. Well, again, let's say that the heater turns on, but it stays on until the temperature in your house gets actually above 72. And then it turns off, and then as the temperature in your house starts to drop, it's actually got to drop below 72 before the heater will turn on. It doesn't, in fact, usually it's got to drop maybe 1 or 2 degrees below. Have you ever set the temperature of your home, maybe whatever it is, 72, 68, and either you felt kind of it was too warm or too cold, and you went and looked at the thermostat and it's set for what you wanted to, but the heater hadn't yet turned on, or the air conditioner hadn't yet turned on, because it's got to go about 1 degree or 2 degrees either below or above what you set it at before the heater's turned on or the air conditioner's turned on. So that's why we say it kind of oscillates around 72. This is exactly how our body works as well. The fact that our set point is 98.6 does not mean that our body temperature stays absolutely perfect at 98.6. we actually have to have our body go above 98.6 before our temperature control center activates the cooling mechanisms. And our body temperature has to go below 98.6 before our temperature control center activates the warming mechanisms. All right, so what are these cooling and warming mechanisms? So on page C15, we wrote what I've just told you. Whenever your body temperature becomes lower or higher than the set point level, the TRC, you'd say, what's that? That's the Thermoregulatory Reflex Center, activates the effectors, the organs to compensate and return the body temperature back to the set point. All right, what are the homeostatic reflexes that are activated whenever your body temperature becomes lower than the set point? These are the heat generating mechanisms. Now, the very first thing that happens when the temperature of your body becomes lower than the set point is you feel cold. Now, you'd say, well, what's that going to do? The fact that I feel cold, how's that going to help me? And the answer is, we're humans, not dogs. You'd say, yeah, so what? If you're cold, you might put on a sweater. If you're cold, you might put on a jacket. If you're cold, you might make something hot to drink, a hot cup of tea. And then your body doesn't have to do anything more. Because we're smart enough that if we feel cold, maybe we'll simply go and do something to warm ourselves up. So we don't have to start shivering or anything else. Dogs can't do that. Dogs don't say, I think, I'm cold, I think I'll put on a sweater. I'm cold, I think I'll make myself a hot cup of tea. So they have to rely entirely upon the physiological mechanisms because they don't have behavioral ways to adjust. We can behaviorally, when we're cold, do something about it. And maybe that's sufficient. Maybe that's sufficient to warm us up so we don't have to do anything more. If it's not sufficient, on the next page, then our body starts, our temperature control center starts doing things to help us. The first thing it'll try is it'll cause the blood vessels in our skin to constrict. We've said that if the blood vessels in your skin constrict, that reduces blood flow to the skin, and decreased blood flow to the skin should reduce radiative heat loss. This is what we were talking about where I've just reviewed it. That'll reduce radiative heat loss. And we've talked about this. If you immerse your hands in icy cold water, it'll look like all the blood went out of your hands, your palms of your hands. So all of a sudden it just looks like there's no redness to it. It looks totally pallid or pale. And that's the vessels, that's the temperature control centers constricting the vessels in the skin and reducing the flow of warm blood in your hands to reduce heat loss through that cold, icy cold water. Now, if that's still not sufficient, then your temperature control center, and these are all mediated by the nervous system. The nervous system is what's causing the blood vessels to constrict. The nervous system is what's causing the skeletal muscles to shiver. So these things happen right away. Your temperature control center sending signals along the nervous system, the motor pathway, will activate your skeletal muscles to start contracting. Contracting of your skeletal muscles increases heat. How does it increase heat? Using your muscles? Contracting?
Friction, the shaping of the bone.
Okay, friction and increased cellular respiration. Now the increased cellular respiration is actually even more important than the frictional heat, but frictional heat contributes. Now, comment I do want to make, whenever you're chilled and you do start to shiver, you can stop shivering anytime you want. Did you know that? Has anybody ever been shivering? Right? So you're thinking, how can I did you try stopping it?
No.
Okay, here's how you stop it. All that your temperature control center wants you to do is to use your muscles in your body to generate heat. So if you just start running in place, you start doing calisthenics, the moment you start moving, you'll stop shivering, I promise you. The idea of shivering is what I call an idiot override. Why do I call it an idiot override? If somebody's going to sit here going, oh, I'm so cold. Look, I'm so cold, I'm shivering. But you're such an idiot, you're just going to sit there and shiver. Then your brain says, you're an idiot, we're going to make you use your muscles. even though if you're not going to do this voluntarily, if you're not going to voluntarily use your muscles to generate heat, then we will make it occur involuntarily. And there's a number of these things where your body will make you do something that you are not electing to do on your own. There's a number of things. There's another example of an idiot override. That's my term. That's not the book's term. Is if you ever take a kid, 7-year-old kid, to Toys R Us. All right? So what does a 7-year-old want at Toys R Us? They want everything. They want everything. Mommy, I want that. I want that. Mommy, can I have that? I want that. Mommy, this one. I want that. What happens if you say no? They can have what's called a temper tantrum. All right? And they fall onto the floor, and they start screaming, and all the other customers think you're killing your child. All right? And then they hold their breath, right, in a temper tantrum. Have you ever seen that? So the kid holds their breath, and they're now turning blue. So you're such an evil parent because you said no. They're going to go and commit suicide, right? They're going to hold their breath and die. So you cannot commit suicide by holding your breath. Because at a certain point, the idiot override in your brain says you're an idiot, and it forces you to breathe. These first three things that we've mentioned, that when your body temperature becomes lower than the set point, you feel cold, and behaviorally maybe you can warm yourself up. Or, if that's not sufficient, the blood vessels in your skin constrict to reduce radiative heat loss. Or, if that's not sufficient, shivering to increase muscular activity to generate heat. Those all occur very quickly because all three are mediated by the nervous system. Now, we know there's another way to affect changes through the release of hormones. Hormones take longer to work because hormones have to be produced, secreted into the bloodstream, circulate through the bloodstream, and affect changes in the cells of your body. So these are slower changes that don't occur immediately. But when we are repeatedly exposed to a cooler environment, our temperature control center causes our thyroid gland and our adrenal gland to start secreting more thyroxin and adrenaline. Now, the thyroxin, the function of thyroxin, the role of thyroxin and adrenaline have very different roles in our body. But both these two hormones have one thing in common. Both these hormones increase our metabolic rate. They increase the rate of biochemical reactions in our body, including cellular respiration. And therefore, they increase heat production. So when we're repeatedly exposed to a cooler environment, we start to secrete more thyroxin and adrenaline, which speeds up our metabolic rate, increases the rate at which we break down food into energy, and generates a lot of heat as a byproduct. This is part of what I wrote is called acclimatization. Acclimatization. And you might say, what is acclimatization? Acclimatizing? So right now, we're approaching the fall, right? It's been the summer and we're approaching autumn. The days are getting shorter, right? The sun is setting sooner and sooner. And it's getting it wasn't very cold last night, but the days will start to get a little bit cooler. And as the days start to get cooler as we move towards winter, and again, LA doesn't really get that cold, but this repeated cooling trend will cause an increased secretion of thyroxin and adrenaline by our body to increase the breakdown of food for both energy and heat production. Now, on the other hand, in spring, as the days become longer and warmer, and we start to move towards the warmer summer months, so then it's just the reverse. We start to secrete less thyroxin and less adrenaline to decrease metabolic rate, decrease production of heat. This is part of acclimatizing. If you wanted to shock your body, really suddenly, just relocate to Anchorage, Alaska, right? So tomorrow, fly up to Anchorage, Alaska. Because right now it's, we've got nice pleasant days of in the mid-70s or something, or low 80s. All right, so Alaska, it's already getting down into the 50s. All right, and in a few more months, it'll be down around 0. All right, that'll shock your body, and that'll cause significant increase secretion of thyroxin and adrenaline to break down food at a faster rate for heat production. All right, so that's how our body adjusts. In other words, if you've ever moved to a different location with a different climate, Maybe you found it too cold, maybe you found it too warm, and then you notice over a few number of days or weeks, you start to get, quote, more used to it. And that's not just because you're psychologically adjusting, you are physiologically adjusting to that changing climate. All right, now we've been talking about the 4 things that occur when our body temperature becomes lower than the set point. Now, on page C16, let's identify what are the homeostatic reflexes that are activated whenever our body temperature becomes higher than the set point. Or if our body temperature becomes higher than the set point, we've got to cool off. So the homeostatic reflexes have to act to cool us down. Now, the first thing that happens when your body temperature becomes higher than the set point is you'll feel hot. So again, your first thought is, what will that do? Okay, fine, I feel hot. Again, we are humans, not dogs. If we feel hot, you may take off your sweater. You might turn on a fan. You might make yourself an ice cold drink. You might just open up a refrigerator and stand in front of it. But if that's sufficient to cool you down, you don't have to do anything else. Then you don't have to sweat, and you don't have to go and do all these other things, because you've behaviorally made the modification. If that's not sufficient, the control center, the thermostatic reflex center, will, via the nervous system, cause the blood vessels in your skin to dilate. Dilating the vessels in your skin increases the flow of warm blood to the surface of your skin, increasing radiative heat loss. Exactly what we spoke of earlier today. If that's not sufficient, your temperature control center will activate your sweat glands via the nervous system and cause sweating. And that increases evaporative heat loss. Remember, sweating only cools you down if the sweat evaporates. Now, those 3 things occur very quickly because they're mediated. They are controlled by the nervous system. But if we're repeatedly exposed to a warming climate, then we start to secrete less thyroxin and adrenalin, decreasing heat production. And that's part of acclimatizing or physiologically adjusting to a warming climate.